So we talked about those measures of center, those estimates of center. And we looked at the mean and the median are definitely the best, and the median is generally considered to be the more stable. So the median is what we would normally consider the best measure of center. Now we need to talk about those measures of spread or dispersion. So when we're looking at those measures of spread, probably the easiest one we can use is something called the range. Spread or dispersion. The range, very similar to the mid-range that we discussed for measures of center, is simply just the largest number, the maximum, minus the smallest number, or the minimum. So I'm going to put another small set of numbers up here. And I'm going to put them in order from smallest to largest just to make it easier on me. So there's a set of numbers. The largest number there is 30. The smallest number is 14. So our range is 30 minus 14, or 16 is the range. Well, you look at that, that's not a terribly useful value. I could have other sets of numbers. In fact, I'll put another set of numbers up here. Oops. Let me do this like this. There's one. For this one, the range is exactly the same. The range is 14 to 30, or 30 minus 14. It's going to be 16. But I would say that this red one is a lot less spread out than the green one is, because all the numbers are right in the middle at 22. So the range is not a great measure of spread. The measure that is much more useful, much more powerful, is something called the standard deviation. It's also much more complicated to calculate. I'm not even going to write the formula down for you to use because it's just not worth it. The formula is too complex. What we're going to do is we're going to give you a step-by-step process for finding standard deviation. Step 1 is to find the mean. So we're going to use this green set of numbers first. Its mean, if I add them up, 14 plus 19 plus 21 plus 26 plus 30. There's 5 of them, so we're going to divide by 5. What is that? 40, 80, 110 divided by 5 is 22. That gives us a mean of 22. Step 2. Subtract the mean from each value. So we have 14, 19, 21, and 26. And 30. And we're going to subtract 22 from each of those. So 14 minus 22 is a negative 8. 19 minus 22 is a negative 3. 21 minus 22 is a negative 1. 26 minus 22 is 4. And 30 minus 22 is 8. Now at this point, if we were to add these up, it should add up to 0. Now that's not really a significant thing. It's just a way to double check yourself at this point to make sure you've done things okay. The third step is to square each of those numbers. Negative 8 squared is 64. Now here's a word of warning. When you punch this into your calculator, many of your calculators will try to tell you that's negative 64. What you have to do in your calculator is you actually have to put the negative 8 inside parentheses and then do the power of 2. Otherwise, what it does is it squares the 8 and puts the negative back in front of it. Any number squared should be positive. So when you square a number, the result better be positive every time. Negative 3 squared is positive 9. Negative 1 squared is 1. 4 squared is 16, and 8 squared is a 64. Step 4. Total those up. Add those numbers together. What do we have? 80, 90, 154 is the total. Step 5. We're going to divide by n minus 1. What's n for this data set? 5. So n minus 1 is 4. So you're going to divide by 4, which is going to be, what, 38.5, I believe. There it is, 38.5. By the way, if we stopped here, this number would be what is called the variance. The next step, step 6, square root. So the square root of 38.5 is 6.205. 6.2, we'll just call it. There is our standard deviation, 6.2. What that is saying is, on average, the numbers in this list are about 6.2 units away from the mean. Now let's go back and do this list. 14, 22, 22, 22, 30. Step 1 is to do what? Find the mean. The mean of this, punch it in, divide it out, is 22. By the way, if you're punching it in your calculator, you add them together, hit equals before you divide by 5. Otherwise, it'll mess you up. Hit equals and then divide by 5. What is step 2? Subtract the mean from each value. Very good. Well, we're subtracting 22 from each of them. 14 minus 22 is a negative 8. 22 minus 22 is 0. Still 0. And still 0. 30 minus 22 is 8. What is step 3? Square each. So negative 8 squared is 64. 0 squared is 0. 0 squared is still 0 and still 0. And 8 squared is 64. Step 4. Add them up. 128. Step 5. Divide by n minus 1. Well, n is 5, so we're going to divide by 4. 64, 32 we get. And then step 6. Step 6, last step is square root. So the square root of 32. 5.66. And in the instructions for any problem, it'll tell you where you want to round it off, whether it's rounded off to the nearest 10th or 100th. Here we rounded to the nearest 100th. Any questions on standard deviation? It's a long process, but it's not that bad. On the test, I would never do more than 7 or 8 numbers. I'm not going to give you a list of like 20 of them and tell you to do it. So what is all this good for? Why do we care? Well, I'm sure.
On step 5 where you have 5 divide, is that n minus 1?
That's n minus 1, yeah.
Thank you.
So what is this information useful for? Well, we go back to the bell curve. On our bell curve, it just happens to be that the mean and the standard deviation divide up our bell curve into set segments that are the same no matter what population we're looking at. If the center of this, of course, is the mean, And we go out in steps of 1 standard deviation at a time. So this is minus 1 standard deviation, or 1 standard deviation below the mean, minus 2 standard deviations, and minus 3 standard deviations. Going this way is plus 1 standard deviation, or 1 standard deviation above the mean, plus 2, and plus 3. In these spaces, there are set percents. 34% of the data will be between the mean and 1 standard deviation on each side. 13.5% will be between 1 and 2 standard deviations away from the mean.
Are these just standard?
These are standard. These percents are the same on any curve. 2.35% is between 2 and 3 standard deviations. And 0.15% is outside of 3 standard deviations. Those percents never change. What changes are these numbers down here. To find those numbers down there, we need to know the mean and the standard deviation of the population. Let's say you're looking at cholesterol. I can't even spell it. We'll just say you're looking at cholesterol. I'm not going to write it down. Let's say that the mean for a given population, cholesterol level, my connection is doing funny things again here. Let's say the mean cholesterol level is 125. I'm going to keep it a nice round number. And there's a standard deviation of 25. Actually, let's make it 30. Okay. What that means, the middle number here, 125, is the mean. Now as we move down to the left, each step we're subtracting a standard deviation. So we're subtracting 30. 125 minus 30 is 95. Minus another 30 would be 65. And minus another 30 would be 35. Going the other direction, we would add the standard deviation. So we'd add 30. So 125 plus 30, 155. Another 30 is 185. And another 30 is 215. So what does this tell us? Let's say we wanted to know what percent of people in the population had a blood pressure, or cholesterol of more than 155. Well, we look up here. Here's 155. More than would be on this side of it. We just add up those numbers. If we add up 13.5, 2.35, and 0.15, we get 16%. 16% of all people have cholesterol above 155. Let's say we want to know what percent have cholesterol less than, let's do 65. Well, now, this time, here's the 65. Less than's over here. If we add those up, 0.15 and 2.35, that's 2.5% of people have cholesterol below 65. Does that make sense? What if I asked, how about between 95 and 155? There's 95, there's 155. Add those up, 34 and 34 make 68%. So 68% of the people are between 95 and 155. Does that make sense? Like I said, those percents never change. Let's say that you're looking at buying a house. And you decide you want a 3-bedroom, 2-bath house. And you do some research and you find that in the area you're looking, houses that are that size, that are for sale at least, or that have sold that are that size, have a mean selling price of $140,000. And the selling price has a standard deviation of $25,000. So on our curve, what number is going to go right in the middle here? 140,000. I'm just going to write 140. The next notch over would be, we subtract 25. Yep. So it'll be 115. 140 minus 25 is 115. And then subtract another 25 would give us 90, and subtract another 25 would give us 65,000. Going this way, we're going to add 25. So this will be 165,000. This will be 190, and this will be 215. The percents are still the same. Oops, 35%. As I said, these percents never change. They are constant. There are some textbooks that give you these are rounded numbers. There are some textbooks that give you more exact, like 34.13% or something like that. We're not going to be that technical. We're just going to stick, this is called the approximate normal distribution. We're going to stick with that. So let's say you find a house that you just love, and it's priced at $190,000. Is that a good buy? Well, you look here, here's $190,000. And if you add these percents up here, what you find is only 2.5% are more expensive than that house. In other words, 97.5% of houses that are 3-bedroom, 2-baths are cheaper than the one you're looking at, which is telling us that there's a good chance you can find one you like that's cheaper than that. Make sense? Okay. Now this mean and standard deviation can be used for something else as well. There's something called a Z-score that allows us to compare. This empirical rule, it's called, with the bell curve up here, is very useful. But if numbers don't fall right on a standard deviation, let's say it was 170, well, that's somewhere in here. This doesn't help us a whole lot because it's not right on one of our set marks. Well, Z-scores allow us to be a little more flexible. A Z-score is a number minus the mean, and then that difference divided by the standard deviation. Let's take a look at an example of this. I'm trying to think of one in the medical field, but I'm blanking out right now, so we'll just go with a standard one in merchandising. Let's say that you manage a department store, and you have to get rid of an employee. You have to fire your employee. You've narrowed it down to 2 people that are the worst salespeople. One works in toys, and the other works in electronics. What you've decided to do is you're going to give them each a week, and whoever has the worst week is gone. Well, the person in toys has a week where they sell $1,800 worth of merchandise. The person in electronics sells $2,400 that week. So that means the toy person is gone? Say no. 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 Why? Well, you told me to say no. Electronics are more expensive and they're in more demand. Let's look at all salespeople in toys. And we find that that week there was a mean of $2,700 in sales. And a standard deviation of $300. For electronics, all of the salespeople in electronics, let's say they had a mean of $3,150. Oops. Let's do this. I mean a 3,200, I should say. And a standard deviation of 250. Let's calculate a Z-score. The Z-score for this person will be their sales of 1,800 minus the mean for everybody of 2,700 and then divided by 300. 18 minus 27 is 900. Divided by 300 is 3. Actually, it's a negative 900, so divided by 300 would be a negative 3. So that has a z-score of negative 3. What that means is this value is 3 standard deviations less than the mean of 2,700. Let's do this one. Z equals 2,400 minus 3,200 over 250. 24 minus 32 is a negative 800. Divided by 250 is a negative 3.2. This person was 3.2 standard deviations below the mean. Who is worse? The electronics person is gone. They are more standard deviations below the mean than the person in toys. Let's do another example. Let's say you're doing performance evals and you want to evaluate the best person. And you have a performance score that you give each of them. Employee A and employee B. Let's say employee A gets a performance score of 32. And employee B gets a performance score of 28. But here's the thing, they work in different wings, different departments. Maybe one's in the maternity ward, one's in ER, or whatever. So we have to, again, compare them to the people that are in the same conditions. So let's say that all the people in the same area as person A, let's say they have a mean of 26 and a standard deviation of 3. And the people over here for B, they have a mean of, let's say they have a mean of 24, a standard deviation of 2.5. So let's find our z-scores. So what are we going to do to find the z-score over here? Perfect. 32 minus 26 divided by 3. So 32 minus 26 is a positive 6. Divided by 3 is a positive 2. This person is 2 standard deviations above the mean for their group. How about this one? What are we going to do? (28 minus 24) divided by 2.5. So 28 minus 24 is 4. Divided by 2.5 is 1.6. This person's only 1.6 standard deviations above the mean. So employee A is the better employee. What do you think? Good stuff? Well, there's homework on this. It's in your homework sheet in Blackboard, so I'm just going to list out the page numbers for you. Page 321, 326, 339, 347, 353, 357, and 359. Next week is our test on statistics. That's all we're doing next week. Should be plenty of time to ask questions before. The statistics test on average takes people less than an hour to do.